Welcome to the course on power quality. So, we will like to cover today improved power quality converters, AC/DC buck boost converter. We will start with the outline, having introduction, classification of buck boost improved power quality converter, then principle of and control of buck boost converters, analysis and design of buck boost improved power quality converters, and modeling and simulation and performance of buck boost improved power quality converter. Numerical examples, summary and followed by references. Well, the objective of this lecture is considering the requirement and applications of a buck boost improved power quality converter. Then we will like to give a configuration and classification of buck boost improved power quality converter. Then we will talk about control of buck boost improved power quality converters, like to analysis and design of buck boost converter, then modeling and control of buck boost converters. So, well, coming to this buck boost improved power quality converter, I mean it offers wide input and output voltage range, operating capability, and they also provide high power factor at supply side, and they have a natural protection against inrush current, and they have a high performance characteristic during startup and overload conditions, offers low electromagnetic interference with the proper design AMI filter, and they have a easy implementation of transformer isolation, high frequency transformer isolation, and they provide better input output current ripple characteristic, and they have efficient operation, and they provide wide range of application from phi watt to phi kilowatt. So, some of the applications of these buck boost converters are like electric vehicle battery chargers, which are coming big way for different rating electric vehicle, like maybe like a two-wheeler chargers, then three-wheeler chargers, four-wheeler chargers, then the electric drive system for like a PMSM drive, then synchronous motor drive, permanent brushless DC motor drive, then lighting system like a LED bulb, street light, highway light, T8 tube light, and luminaries and flood light. I mean, with of course, because this all LED light needs the DC supply, and which we can get certainly from AC supply by using these you can call it buck boost improved power quality AC DC converters like. Then telecom power supply, I mean they also need the DC supply. Then the domestic home inverter and uninterruptible power supplies. Then computer power supply, welding machines which uses very high frequency transformers, I mean, and it facilitates for that conversion. And of course, some of the more applications are like wireless power transfer, again for charging and for other applications. Then more electric aircraft, traction system, home appliances like air conditioner, LCD display, washing machines, and HVDC, and many more. Well, coming to the classification, we classify based on supply system, like maybe these buck boost improved power quality converter can be classified on basis of like single phase and three phase. And in single phase, we can also again have a power flow directions like maybe unidirectional and bidirectional, and for three phase again unidirectional bidirectional. So, structure based classification, of course, we talk about with the based on non isolated and isolated. In many applications, we use of course non isolated topology, I mean like which requires, I mean this DC supply, maybe constant or variable DC supply, and of course, for isolated configuration there are plenty of applications, because all these electronics gadgets which we are talking about, some of them they need the isolated supply, and of course, in for providing isolation we have the high frequency transformer, of which the size, cost and weight are also reduced, and efficiency also increases like. So, for of course, the configuration in the non isolated category can be further classified, like you are using bridge type structure. Bridge in the sense we are using from even from single phase AC supply, we are taking like a typically a diode bridge rectifier for conversion of AC to DC, or we are using semi bridgeless, or we are using fully bridgeless configuration of input rectifier like. In the isolated also we have again same bridge type or semi bridgeless or fully bridgeless configuration like. There are plenty of topology. The classification based on the topology, we can call it like a conventional buck boost converter, then derived buck boost converter, then single ended primary inductance derived buck boost converter, then jitter derived converter, and canonical switching derived buck boost converter. And the basically classification based on the design and control, we call it like a buck boost improved power quality with continuous conduction mode control, of course, which the design is much different than what we go for buck boost improved power quality with discontinuous conduction mode control. I mean, like, so even design have to be different, then that's the reason control have also to be different in both cases. And then buck boost improved with the critical conduction mode control, or it also called boundary mode control, or we call it like a typically, I mean, the intercepting of both the control. So, coming to typically first category of single phase buck boost improved power quality converters. So, the simplest topology is like we use the single phase cascaded unidirectional buck boost converter. So, what is we do in cascaded? First we are having like a, of course, with the MI filter we are putting first buck converter and then followed by the boost converter. I mean, typically here, of course, this inductor is sharing for both buck boost converter, but in this case we are using the two devices, like I mean here. Of course, the benefit of this converter that the stresses on both the devices are much less, I mean, in this configuration, like I mean. So, what we are doing cascading of buck and then boost, like as the name suggests, like. But of course, it is also practically possible, but of course, here we have a even the polarity, you can call it with the plus minus here, I mean, like. But there is a, of course, it can be a single device, a single phase unidirectional buck boost converter, as you can see it here. So, the benefit here is only you are using one device. So, you are able to eliminate virtually one device and one diode in this configuration compared to the upper configuration. But the disadvantage is that the polarity is reverse here, and the second disadvantage is that the voltage across the device is the sum of input and output voltage, which was not the case in previous one also. Of course, you can design this inductor either continuous conduction mode or discontinuous mode or boundary condition mode. That is the basis we divided the control in that case. Like coming to like a, of course, single ended primary derived single phase unidirectional buck boost converter. I mean, here of course, we have it's also called fourth order. So, we have a like input inductor, output inductor. Of course, EMI filter there, either you can keep it here or you can keep EMI filter here, and here the of course, you have a typically two inductors, and then you can you have a output. Of course, here the polarity is not changed in this case. Now, you have a mini design for, you can call it for DCM, because now you have a three component with the energy transfer L1, Li, Lo and capacitor C1. So, now you can think about like total design corresponding to DCM and CCM may be 2 to power 3, the 8 design. And you can have all DCM, you can have all CCM, these are the two exclusive design, but you can have only one component having a discontinuous variable, like either in the inductor it will be discontinuous current or it can be like a continuous current into that. Similarly, capacitor also you can have a discontinuous voltage across the capacitor or you can have a continuous voltage across the capacitor. So, like this you have a 2 to power 8 design and you select the best design which is acceptable to you for particular application like. So, if we talk about in DCM for inherent power factor correction, normally we prefer typically output inductor current discontinuous. The reason being that if you take input inductor discontinuous, the size of EMI filter will increase. But if you take a voltage across the capacitor discontinuous, then the voltage across the device and currents, especially the voltage stress across the device and diode increases substantially very high. So, you have to select the voltage rating quite high like also. So, these are the relative merits and demerits of course of these design, and of course, the another is the CUC derived single phase unidirectional buck boost converter. So, in CUC also number of component in SEPIC and CUC are same, as you can see input output inductor, and this is the, you can call it the capacitor energy transfer element, but here the drawback is the polarity of the output voltage reverses here like but originally the CUC had developed it to make this input inductor and output inductor almost continuous current. It also called that it should be noiseless converter, and it should not have a noise. So, inductor current should be almost constant in the input and output, like of course, in CCM you can operate that mode also, but the size of the inductor will be substantially large. So, people have not thought how really this converter, even a CUC have not thought that how the people will be operating this converter for different applications now. So, you again you can have even a 2 to power 3 design like gate design, because you have a 3 element for which you can have a every element either voltage or current discontinuous. I mean capacitor voltage can be discontinuous. Again this also, if very voltage high voltage stress across this, if you are taking capacitor voltage discontinuous across capacitor, or you can have a inductor current discontinuous, then you will have a typically the size of EMI filter will increase. But if you take a output inductor discontinuous current, of course the other though merits of compared to other design certainly is better in this case, like or so. So that is another like for with power factor correction. And the third is the canonical switching derived converter. I mean like here you can say, here also you can think about this is the energy transfer device. So if you can make it typically this current inductor current discontinuous, then we call it DCM mode of this converter, and or you can have a continuous conduction of this. So that is also a simple, I mean as have been simple buck boost. So this is also a simple design of this buck boost converter. All these are buck boost, means output voltage can be buck reduced or it can be increased, like so can be provided even from 0 to even a higher than the input voltage in this case all these, and while maintaining the power quality or power factor close to unity on the supply side. Then this is the jitter derived again buck boost converter. Here also you have the same number of element as the Cuck Sepik, I mean Cuck and Sepik, and here also energy. So you can design again 2 to power 3 design here also, like I mean typically of this, like, and all. Of course the drawback of this, that device is coming in series, so you will have a input current discontinuous. So you can keep the EMI filter, but the size of EMI filter certainly increases. But the one major benefit compared to other topology is that your quality is not changed here. I mean like, so it depends on relative merits and demerits of all the topology, like I mean also. Then this is single phase buck boost improved power quality converter with the bidirectional converter. Buck, I mean you can put the power from input to output, output to input, but you can clearly see here, I mean this is nothing but a modified version of, because there is not much requirement of such nature, but it's indirectly you can call it is a matrix converter. So you can have a unity power factor of course on the input supply side, okay, and for the input it becomes like a, it work like a kind of output as a inductor is there, so it will work as a current source converter. For input it works like a voltage source. So this converter can have a both features, but you can understand number of components here are quite large. You need the bidirectional switches, so you require like almost 8 MOSFET or 8 IGBT for that, like, but of course circuit concept is possible, but of course you can understand, I mean like we will have derived other topology also, but this is one of the topology for bidirectional buck boost converter, like. So coming to like analysis of these single phase buck boost converters. So let us take first simplest case of your taking example of single phase buck boost converter. I mean, so it can provide the step down output voltage or even a step up voltage. So you can vary the voltage over a wide range. I mean you can have typically, because of this reason you can have a input voltage even universal AC mains, which we call it like a 0 to 70 volt. Still you can have a power factor correction, and output voltage can be even controlled from 0 to maybe 300 even 400 volt or so with the help of this converter. So that is the wide flexibility. Only the disadvantage here is that the voltage across the device is the sum of input output voltage. So that you have to select the device for quite high voltage rating, like. So the output voltage can be higher or lower than the input voltage, and it is used in regulated DC supply where the negative polarity output may be desired with respect to the common terminal of the input, and the output to input to ratio, because it is a buck boost converter. So you have this kind of relation which give you, if duty cycle is below 0.5, it give the, typically you can call it like a buck operation. If duty cycle is above 0.5, it gives the boost operation, like I mean at 0.5, I mean it input output voltage will be typically the same, like you can just see from that relation. So this allow the VO to be higher or lower than the VD, like of course it is a opposite polarity, so normally people write a negative sign with the here. So this buck boost converter, if we talk about first in continuous conduction mode for the analysis of this. So when switch is on, diode is reverse bias, as you can see here. I mean like you are just shorting the inductor input supply with the inductor, and this output capacitor is giving the energy to the load or power to the load, and circuit is isolated and inductor charge. So you can call it input voltage, which is rectified diode voltage will be applied across the inductor. So you will be increasing the inductor current, and when switch is off, then this inductor current cannot be quenched quickly, which was already flowing in this direction. So it cannot be quenched quickly. So, you will find the inductor energy goes to the capacitor, I mean like with this typical relation that so inductor getting here inductor was charged, capacitor was discharged, here inductor is getting discharged, but capacitor is getting charged like I mean also here typically. So, their role reverses like, and of course, we can have a inductor current flows continuously in continuous conduction mode. As you can see here, we apply the across the inductor the input voltage and the current increases, and when we switch off the device the diode conduct. So, we apply the output negative voltage, but the output voltage may be lower, so current reduces like. So, that is the process it goes, and taking average inductor voltage which should over a period must be 0. So, you can keeping equal to 0, that is for on period, this is for off period. So, you will get this relation output upon input will be d upon 1 minus d, which give the relation corresponding to buck boost operation, and if d is your less than 0.5 it give a buck operation, if it is a d equal to above 0.5 then it give a boost operation. So, assuming the considering the lossless component, so we can say input output is same power, and from this you get a current, I mean for current relation is just inverse of this relation. So, depending upon the duty ratio the output voltage can be either higher or lower than the input voltage, and considering the eta percentage a current ripple in the minimum inductor for continuous current conduction can be calculated from this relation, from the same as we got typically from period corresponding to turning on, and where d is the on duty ratio and f is the switching frequency. Considering the slow varying voltage ripple at the output side DC link capacitor, I mean like because it is a second harmonics will be there. So, you can find out the output capacitor. So, inductor is calculated from here, capacitor is calculated from here, like from these two relations that give you the value virtually for the inductor and capacitor in this converter like. So, coming to now the single phase buck boost AC DC converters with high frequency isolation, transformer isolation. We already discussed why we did the isolation. The very purpose of this isolation in the here we have shown one output, but you can have a multiple output, I mean like which give you multiple DC supply also. Of course, one have to be closely tightly regulated, but other can be typically like you can call it is followed by the turns in the transformer. So, coming to the first like which is a derived topology from simple buck boost converter. So, here we are using that inductor as a coupled inductor, or you can call it, people call it flyback inductor or coupled inductor, I mean where the of course, one winding will have at one a time, that is the reason we call it the inductor. So, here also I mean if you are operating with the current multiplier approach and you are designing this typically the magnetizing inductance of this transformer in continuous conduction mode, then you have to use current multiplier approach, that we have reference voltage, feedback voltage, voltage controller, that become the amplitude of the inductor current, and you have a phase from here. So, you multiplied it, so you get the inductor current reference current, and you sense this current here, and that give you the getting signal for the devices. So, this is what we call it, you can call it for continuous conduction mode of operation of this buck boost flyback buck boost converter like. This is the most simplest converter. It is very extensively used from fraction of watt to typically order of a even 500 to 600 watt like I mean also. But major range of this is of course you start I mean like a digital energy meter is a half a watt is the SMPS for which this flyback converter is used, because its usage you can see the minimum number of component like I mean also in this converter like. Now, the second converter of course is the buck boost your Cuck derived converter with the voltage follower approach. So, here what we already discussed. Now, if it is isolated topology, you have a very interesting design. Of course, you want here the perfect correction that supply current should be in phase with the supply voltage. I mean like that is the improved power quality converter you can call it. But now you can understand here, now we have a 5 energy storage element, the input inductor, output inductor. Because of the transformer in between, we divide the energy transfer capacitor in two parts like C1 and C2, and then we have a magnetizing inductance of this transformer. So, now you have a 5 element, and 5 element means now you will be having 2 to power 5 designs, that is virtually you can call it 32 design of this converter like. So, I mean you have to select out of 32 design which one is the best for you. I mean like of course, we look into that. Of course, if you are designing for continuous conduction mode for all the energy storage component like your C1, C2, Li, LO as well as magnetizing inductance, then of course, this is one unique design, all can be discontinuous, that is another unique design, but you can have a one in discontinuous like. So, after going through and but if it is a continuous conduction discontinuous conduction, then only you can use the voltage follower, means only the output voltage loop is required to regulate the output voltage. And we look into several design, and we found if you are keeping a output inductor current discontinuous, that give a best, one of the best design. You cannot say best out of 32, one of the best. And then of course, we have a control here that we are having a reference voltage, we have a feedback voltage, and we have a voltage controller, and this we compare with the, of course, the typically sawtooth wave of high frequency for which the transformer is designed and converter is designed, and then we give the getting signal to this switching device. Switching device, I mean, depending upon low power, it can be like a, typically you can think about it can be MOSFET. High power, of course, we can take the IGBT, but you can understand here this is the one of the best converter in the sense that in this transformer, because of these two capacitors C1, C2, you are not allowing the any DC component to. So, that is the reason for nominal cases we designed this converter around 0.5 duty cycle, because for 0.5 duty cycle, of course, the you can have, but the voltage ratio what for which we are designing, that we can take with the help of transformer N1 by N2. But you can have a multiple secondary also required for many applications like. So, the of course, transformer is providing isolation, another is the major is a multiple output. I mean, with the help of this we are providing, and we are going high frequency to reduce the size of the transformer. So, that efficiency is enhanced, cost is reduced, size is reduced, I mean losses are also reduced in this converter. So, this consider one of the very good converter for the purpose of with the inherent power factor correction also. How curves, so I told you that you can keep any other, but even a single will do that job like. So, coming to like another converter, that is single ended primary inductance converter with voltage follower approach. Again we are designing that we can, in this case, I mean like either we can have a discontinuous I mean current typically in this magnetizing inductor or input inductor or this capacitor like. Okay. And of course, normally prefer to have a minimum discontinuous current in this magnetizing inductance. So, we have a reference voltage, we have a feedback voltage. So, we have a voltage controller, and then we have a typically PWM pulse generator with comparing this output with the sawtooth, and this gives the getting signal. So, it means we are designing either continuous discontinuous current in the inductor or this inductor, but if we design capacitor with discontinuous voltage, then certainly the voltage rating of the voltage stress across the devices goes multiply, as well as the diode voltage also goes, because already otherwise the device voltage is sum of the input and output voltage in all the typically of buck boost converter like also. So, the typically the next converter is single phase like buck boost zeta converter, a series converter with the voltage follower approach. So, here also when you can design either this magnetizing inductance discontinuous or output inductor discontinuous or capacitor voltage discontinuous. So, normally we prefer to output inductor discontinuous, and because of that we can use the voltage follower approach for output voltage control. Of course, in all even inherently you get the power factor correction on the input supply, I mean by design itself. So, you have a reference voltage, feedback voltage, you have a voltage controller, and you compare this voltage controller with the sawtooth to give a pendulum pulses to the device like, I mean also I mean in this zeta converter like. So, coming to this, these are the typically you can think about like four converter flyback, Cuck, SEPIC and zeta. These are the relation for output voltage as well as for magnetizing inductance for DCM CCM, similarly for even for Cuck converter for DCM CCM, and similarly for your SEPIC converter and zeta converter like all these relations for these components calculation, and for of course, in all cases because the output capacitor for the connecting the load have a second ripple. So, that relation remain common for all these converters like. And these are the typical after designing that if you talk about CCM in simple buck boost converter in continuous conduction mode with the same 100 watt load with the 48 volt supply, you can see the TAD in all the 4 cases I mean are lower than typically less than 5%, and power factor is of course close to around unity. With these are the component calculated, those are the relation here component calculated as well as control gains are given here typically like. So, coming to like again this this was in CCM buck boost, and this is the comparison. I mean all 4 you can think about like here, I mean like typically average current, RMS current, peak current, device voltage rating, device current rating, and then the power density, and of course, response. You can call it undershoot, overshoot in the your output voltage like. And then coming to the DCM design for all these 4 converter in discontinuous mode with again 100 watt and 48 watt for flyback Cuck, SEPIC, zeta converter, and these are the TAD of course around in all cases even much less, I mean almost less than 5% and power factor is again close to unity in all 4 cases, and these are the component value with the gains of this even for DCM, where you are avoiding the 2 sensors on the input voltage and current sensing like also. And this is of course the typically you can call it their switch rating and relative switch rating for all 4 converter, as well as switch current rating, voltage rating and transient response like also. So, in no case of course, it is not going to be too much except in JIT a little bit, overshoot little bit more, and these are of course the you can say in CCM continuous conduction mode. In flyback topology you are getting TAD of supply current 3.66%. In case of CUC converter you are getting 4.52%, then SEPIC converter you are getting 4.78 and JITA converter you are getting 3.48 in CCM. And if you talk about design in DCM, for the same power of 100 watt with a 48 volt output, which is very common for many applications, and you get TAD about 5%, and then in this case of CUC you get 4.56 and SEPIC you get 4.91 and JITA you get 4.81 also. So, that is about coming to like now analysis design of single phase buck boost flyback converter, and this is typically the another you can think about the design analysis in DCM. So, here also you have a diode design, you have a flyback with the filter capacitor here and the output voltage regulation with the DCM design. So, and these are the typical waveform, the switch current, your typically diode current and the voltage across virtually across the primary winding, and this is virtually your that was DCM with the you can call it like a your 3 mode. You have a 3 mode here, device conducting, diode conducting, and none of the 3 are conducting. For this duration you have a 3 mode, but in CCM continuous conduction you have a 2 mode, device conducting, diode conducting, and that is the reason you have feedback of voltage, but you have to take a feedback of your even the typically the voltage here as a shaping, and then the current also going to the circuit, and then you have comparing high frequency. So, here you have a 2 mode only, device conducting, diode conducting, but in DCM you have a 3 mode of operation. So, this is typically the analysis of course for flyback. The average current over a switching cycle can be calculated from on period for D period, and this can be like a peak current of half of typically from the triangle area. If you look into the typically in DCM this triangle. So, this is you can call it the area from this triangle, and then you can call it I peak is the peak input current and the D is the duty ratio. From figure you can find out I peak at the end of your on period, and that is the peak current, and typically you can call it where the VLR is the rectified output of diode and LM is the magnetizing. So, you can get I1 from typically from VLR, and VLR is nothing but you can call it like I1 equal to I1 and VL this. So, you can get I1 from putting the value there V1 into this. So, you can call it here this I1 typically keeping the output ratio in terms of this. So, you can find out the from this DCM that duty cycle device conduction, diode conduction will be less than 1. So, that you have a third period which third duration which where none of the 2 are conducting, and you can from this relation you can get a turns ratio also from the output relation and then you can get a even for DCM the minimum inductance also for the relation, and you should keep the inductance lower than that only you will go to DCM. Of course, this you should be ensured at the maximum output power with minimum input voltage, because that will be corresponding to you can call it the maximum current appearing. So, and even at maximum current it should be discontinuous, and of course, the output capacitor is corresponding to your output load current and divide by of course, your twice of the frequency or ripple factor like also. And you can call it the stresses on in DCM will be the peak current of device will be your V1 dTs upon LM, and the switch voltage will be V1 plus eta Vs. So, that is the reason we are calling the sum of input output, but here turns ratio also comes into picture. So, with that it almost comes to double the, and the diode current is there, and the draw you can call it the diode peak voltage will be this like or from this relation. And for continuous conduction of course, you have a very straightforward relation, because you do not have a third mode. The output voltage is in terms of input and the turns ratio there, and the inductance you can find out that minimum inductance. So, you must have a for continuous conduction always the inductance more than that, this is a boundary condition inductance, and the switch of course the peak current, and then the you can call it the switch peak current and then the ripple. So, you can find out the RMS current of the switch, you can call it the your diode current, you can call it the peak corresponding to that, and then you can have a diode RMS current like. So, these are the typical relation to find out all the parameters, or you can say rating of the component like. So, coming to the analysis and design of your single phase buck boost KPC. So, it is like again we were talking about that you are designing in continuous conduction. So, only output voltage loop is required. With the PI you can put a controller here and then compare sawtooth to give gating signal here, and of course, I told you earlier you can have a lot of design, but maybe output inductor discontinuous will be. So, you have here 3 mode: device conducting, diode conducting, and none of the 2 are conducting. And these are the 3 equivalent circuit in all 3 modes. And for continuous conduction mode of this conductive type, again you have outer loop, the voltage loop, then you are sensing the voltage to take a, this is amplitude. So, this take the phase and you have to sense this current, and then you give the compare the error with the sawtooth, and that give the gating signal to this device. So, this is in CCM, and there are only 2 mode in CCM, that device conducting and diode conducting. Here typically your device solid state device MOSFET or IGBT conducting, here diode is conducting. So, you have only 2 mode here typically, and these are of course to simplify the analysis, the quantity are referred to primary side of the transformer. So, volt ampere equation comes typically from. So, this is the voltage transfer to the primary. So, that is typically you can call it the conduction of diode, sorry MOSFET, and this is the diode conduction duty cycle and refer to this, and considering. So, current relation will be just exactly to the opposite to that, and you can find out now typically the first stage of operation, the current which will be sum of the rising current plus initial, because say CCM. So, you will have a then current is starting from minus. So, these are I1, I2, and second stage of operation you can find out typically from these 2 relation like and then you can find out from typically I1, I2, and the summing this you can find out typically this current which is flowing during the this period. So, and you have equivalent inductance for both like. So, these are the, and then by substituting that into you can find out the I1 value, and in I1 you have VLR, you keep the value of VLR. So, you can call it this is following the current in DCM. So, you can call it this is the peak current which is flowing into the circuit, and because this is constant, V1 is peak value of supply voltage, this is your fixed switching frequency time constant, this is the inductance constant, and if you keep the for output voltage duty cycle constant, so I1 will be constant in this relation. So, it means you can call it the input current will be following the input voltage. That is the reason we call it the this voltage follower, means input current follow the voltage in DCM like. So, coming to like a typically calculation of your switch average current or peak current. So, this is the switch average current, you can find out the from virtually a rectangular diagram, and this is the peak current going to be in the switch like and these are the minimum maximum value. Similarly, for diode the average current and peak current, and the switch peak voltage, and the diode typically the inductor you can call it RMS current, average current of the inductor and RMS current. So, this average current and typically the your maximum current in the inductor like. So, coming to now typically design description in typically conversion ratio, that is input output conversion ratio, and you can call it this is the rectified voltage. So, when omega t 90 degree, the conversion ratio obtained as a first step, and here V1 is the peak voltage of input, and second is condition for operation in DCM CCM. So, we to design must ensure DCM operation for which the following relation hold good. So, Ke that should be your 2 m plus n square, and Ke is the conduction parameter, n is the transformer primary to secondary turns ratio. So, from this for CCM you can get this condition should be Ke should be more than this value, and Ke is calculated for minimum value of m occurs minimum output voltage and maximum input voltage in CCM range. So, now equivalent inductance which we already calculated earlier, that comes LEQ as a combination of parallel combination of L1 L2 dash, and where all is the resistance typically of the load equivalent resistance, and then you can find out the duty ratio corresponding to that like. And the annual can be obtained considering a specified for DCM. This is the value which you can get for just DCM as a boundary inductance, where the R is the input ripple and L2 can be obtained from the expression of. And so, similarly for CCM L1 L2 can be obtained from the current ripple relation like. And typically for the energy transfer capacitor like typically can be obtained to, it has a great influence on the input current waveform to avoid current oscillation every half cycle. So, it is given in terms of your you can call it this ripple frequency plus L1 and 2, where your omega r is in between omega L and omega S. The switching frequency, it is a line frequency. So, resonant frequency should be lie between the line frequency and the switching frequency, and output capacitor of course corresponding to all converter is corresponding to depends on the load resistance, and this depends on line frequency and ripple percentage ripple voltage in that like also. So, now coming to modeling and simulation for these all buck boost converters. So, first coming to the flyback converter. So, these are the let us say the a design example that we have a 220 volt 50 hertz and we want 110 volt with the output power of 1000 watt and output ripple 2% and switching frequency 50 kilohertz. First we go to let us say DCM. So, we can have a transformer turns ratio 1.5 to 1 and the calculated by design value LM is for, because it is a DCM. So, we are keeping less than 50 microhenry and L your ripple filter is LF 1 millihenry and 8 nanofarad and output for typically of 2% it comes like a 15 millifarad, and these are the typical result for DCM. You can have supply voltage, supply current in phase and you can see the voltage, ripple voltage is hardly less than 2%, only 1 volt over 110, 1 volt plus minus above and below, and this is in case of CCM. You can see the CCM current is much better than the DCM, voltage and input current, and that is output voltage, and typically this is the, you can call it the total performance. The input current EAD at different load is full load it is 51% for DCM and for CCM is 4.4 and power factor is 0.997, 0.998, and of course, the ripple is also you can call it is much lower, less than 2% what we consider it, and these are the of course, the component rating and typically, and of course, in case of DCM we use the voltage control mode, voltage follower of voltage control mode, and CCM we consider average current control mode like also. So, this is the typical performance relative performance of your all. The major difference in CCM is you can see the current stress at lower, or even in this case also full load also the peak current rating of the device is much higher than the what you have allowed typically 3 times. Similarly, even in case of your diode also it is around 3 times the current rating of the diode as well as the device like and this is of course, after looking the prototype, this is the supply voltage, supply current of this and the power change from 60 watt to 200. So, this is the output voltage and it is a load current which was corresponding to 60 watt then 200 watt and 60 watt again. So, you can see the dynamics, the current remain in phase with the supply voltage and maintaining the unity power factor even during load perturbation also. Now, coming to the CUC converter, that modeling simulation performance of. So, the let us say the input voltage is 160 to 270 volt 50 hertz and the output voltage is also 98 to 132 with the nominal voltage of typically of 120 volt and ripple output is 2% the 50 kilohertz and turns ratio is 1 to 1, and these are the design corresponding to DCM. You can see input inductor 1.5 millihenry, output is 4.3 microhenry, so that we are designing for DCM, and capacitor 2 capacitor on both the side 2.5 microfarad 10 microfarad and the output capacitor is 30 millifarad for the 2% voltage ripple here like. And the performance here for DCM you can see voltage and current input and this is output voltage which have typically less than 1% at 120 output less than 1% voltage ripple like. And this is for CCM operation continuous conduction mode. You can see supply voltage and supply current they are in phase almost like a unity power factor, no harmonics, no reactive power, and output voltage also have a less than 1% ripple in this. And this is the relative performance of this CUC converter. Like this is for DCM, this is for CCM, the TAD value, and typically the power factor closer to, and of course, the peak current in case of DCM is 3 times than approximately 3 times than this your continuous conduction mode. That is one of the drawback of course in DCM for, but the small rating you have a margin in the device rating like. And this is the typically CUC converter rating when we are having a load varying from 60 watt to 200 watt. But you can see supply voltage and supply current is in phase with the supply voltage during even dynamics also or a higher load or lower load, and typically and the controller brings the voltage back to the reference voltage of output voltage of 120 volt. Now, coming to the modeling simulation performance of single phase single handed primary inductance AC to DC converter. If we design typically in your DCM, so we are sensing output voltage and using a PI controller and comparing SAT with this, because we have designed in typically this in DCM mode. also. So, only one loop is voltage follower, it works in voltage follower mode, and you have a 3 mode conduction, device conducting, diode conducting, and none of the 2 conducting. That really we call it discontinuous conduction mode also. And if you have a continuous conduction mode, so we have output voltage loop, then followed by this is the give the peak, we take the phase from here multiplied, so we get a template with that peak, and then we have a inductor current input current sensing, and then using again PI control comparing the sawtooth to give the gating signal to the switch. So, this is for what we call it the current multiplier approach for control in when we design in continuous conduction mode like. And this is we have a typically here typically 2 mode of operation, device conducting, diode conducting, and this is the design with 230/50 hertz 110 volt output with the 1.5 kilowatt 2% here 50% kilohertz and turns ratio 1.1. And here also you can see for discontinuous we are designing output inductor only, this is for continuous conduction, energy transfer capacitor of only 1 microfarad and output capacitor for 2% typically 30 millifarad almost in most of these, and these are the controller gains for this design. You can see the input voltage input current, they are in phase, current is sinusoidal and all phase, so almost power factor unity, and your typically the ripple output voltage is less than 1%, only less than 1 volt, and this is for continuous conduction input voltage input current, they are in phase and current is not distorted, and you have a sine wave current almost line. This is the output voltage ripple less than 1%, and this is typically you can find out the like a THD for DCM and CCM in case of this SEPI converter, and of course, the relative value like a power factor is almost like a unity all case like 0.99 or so more than that like. This is the experimental result for again 60 watt to 200 watt to 60 watt. You can see supply voltage and supply current are in phase, and when you apply typically increase the load from 60 watt to 200 watt, current increases, but remain in phase and current remains sinusoidal also. So, now coming to the modeling and simulation and performance of single phase GTAC AC/DC converter. First we design typically in discontinuous mode by with the voltage follower approach. So, we sense only the voltage and we have a reference voltage, then putting a PI control with the limiter or saturation and compare sawtooth and give the gating signal to for this device of this GTAC converter. And for of course, you have 3 mode, device conducting, diode conducting, and none of the 2 are conducting, that is the zone where none of the 2 are conducting. And if we talk about like a CCM with continuous conduction mode where we have a 2 mode only, so we have to sense typically the output voltage with the reference, we compare, put a PI controller, multiply the phase of this, and that gives the template for with the amplitude of this control output, and then we sense the current input and put a PI control over it, and then compare sawtooth and give the gating signal for switch like in continuous conduction mode. And here we have a 2 mode, device conduction, diode conduction, and you have a here the waveform corresponding to 2 mode. And this is typically the rating again with the 48 volt output 1 kilowatt with the 220 volt 50 hertz and ripple output voltage ripple 2% designed at 50 kilowatt and the turns ratio 5 to 1. And here also for typically you can see here the input inductor we are designing discontinuous mode, output inductor continuous mode typically like output is 10 millihenry, so only input inductor, and these are of course the typically the filter elements like also. And this is the you can say performance in DCM, the input voltage input current which are in phase and the output voltage ripple is less than typically 1%, 2%, and this is the of course in CCM voltage and current, and the output voltage again is hardly less than typically of 1% plus minus like. So, this converter is also developed again for 200 watt with 60 watt load and then 200 and you can see supply voltage, supply current they are in phase, and voltage of course little down, then it settle down. So, but you can say power quality is not affected, it is still have a quite low, and you can see the TAD here also less than 5% in case of CCM and DCM, and of course, the rating which we are talking about is almost like almost double for as far as current stress is concerned or device or as well as on the diode like also. So, coming to typically coming to analysis design and performance of PFC bridgeless buck boost converter. So, this is like a what we were talking about bridgeless simple buck boost converter. So, here you can understand we are sharing a common inductor, in this case the positive half cycle this device conduct and second this device conduct also with this. So, that is typically one configuration. The second configuration of course, we have again 2 devices for positive half cycle, negative half cycle. This is the another configuration of this your buck boost converter for bridgeless configuration, and then this is third configuration for bridgeless configuration also for the simple buck boost, but all have a power factor unity and harmonics also less than typically according to the rating. So, coming to the design, that you have input voltage which is a typically a rectified output of diode rectifier, and you have a relation between input output. So, you can design the inductor in CCM from this relation. For DCM you can design this relation. The inductor should be less than this critical value. If you want to operate in boundary condition, you can take equal to this value, and the output capacitor is in all cases selected this. So, these are typically the they have design equations for getting the component value of input inductor, the inductor in case of this as well as output capacitor also. And these are typical value. This is designed for developed for 350 watt with the output voltage 200 and supply voltage of 220. So, these are the input voltage input current, and this is your inductor operating in discontinuous mode. The inductor for positive half cycle, inductor for negative half cycle. As you can largely see it that how current is discontinuous like, and these are the typically power quality. You can just see here the TAD 4.8%, power factor is unity even for the 316 watt at voltage of 200 correspond to 3 watt typically 350 volt design like. So, coming to like a let's design simulation of PFC bridgeless Cuck converter. This is the typically bridgeless Cuck converter. You can just see here that for positive half cycle this operate and negative half cycle this operate, as you can see from there it is a connection here. They are the input inductors, these are the output inductors, these are energy transfer capacitor for you can call it positive half cycle and negative half cycle, and these are the typical relation between input output, and this is the input output inductor output inductor design for both for CCM continuous conduction mode depending upon the cycle which you are getting from output input relation, and this is the input inductor for positive negative half cycle, and of course, for critical mode for output inductor is the relation this. So, if you want to operate in critical conduction you can take this value. If you are operating in typically of discontinuous mode, then you have to take much lesser than this value, like you will have taken 1/3 1/4 kind of value correspond to what you are calculating from here. And this is the input inductor typically for DCM. This was CCM, this is for DCM, and this is the output of course the intermediate capacitor C1 C2 for both half cycle, like it depends on the voltage ripple, output voltage and duty cycle and equivalent load resistance and switching frequency. So, all these components certainly you can understand inversely proportional to switching frequency. So, if you increase the switching frequency, all these inductors as well as capacitors are reduced, like. So, they are affected by switching, and this is the output capacitor again from load current divided by twice the frequency, because second harmonics get reflected on the DC link, like also. And this is virtually the conceptual waveform, that you have a input voltage, you have a input inductor for positive half cycle, negative half cycle, they are in continuous mode, and these are discontinuous output inductor discontinuous mode, and capacitor for positive half cycle energy transfer, negative half cycle in continuous mode, like also. And these are typically the performance, simulated performance of 500 watt and 300 volt output and 220 volt input. So, you can see input voltage, input current, they are in phase, and current is almost like sinusoidal with the TAD of only 3.56%, this current typically here, and this is virtually input inductor positive half cycle, negative half cycle, which are continuous, and this is the capacitor voltage for positive half cycle, negative half cycle, which are also continuous, but the output inductor current for positive half cycle, negative half cycle, they are discontinuous. So, it says the design waveform you are getting to correspond to what you are really applied the design for, like. And this is of course, the developed circuit for 500 watt with output voltage 300 volt and 220 volt input. So, this is your input current supply voltage, and your inductor current typically input inductor current, and these are the typically your capacitor voltage with the voltage, both are continuous, and then this is your output inductor current which are discontinuous for positive and negative half cycle, and these are the switch voltage stress and diode stress, and these are typically the performance. So, you can say TAD is only 3.8% for 510 watt and power factor is unity, and you can see the supply current and supply voltage, they are in phase, and current is almost like a distortion free with this 500 watt design of this bridgeless Cuck converter, like. This is another topology of power factor bridgeless Cuck converter, typically again for positive and negative half cycle, and then this is another topology, third topology. There are a lot of topology which are there with the power factor correction on the supply side for all these. The third topology, then fourth topology of the Cuck converter, they people modified according to their application requirement, like also this converter. And here output inductors here, so input and output inductors are here. Only what we are including here, even the output diode is also here, only what we are adding there, only the typically kind of the devices for positive and negative half cycle. So, a lot of innovative technology have been, the topology have been there for all these converters. This is the fifth topology of converter for bridgeless version of that for power factor correction also. So, coming to like analysis, design, simulation and performance of your bridgeless SEPIC converter. So, this is the SEPIC bridgeless converter, that positive half cycle and negative half cycle, these are the two. So, this is with this inductor and capacitor positive, and this is for negative half cycle, and these are the relation, that output voltage relation, the output inductors for positive and negative half cycle, then the input inductor positive negative half cycle, and then this is for critical mode, or you have to keep for DCM less than that, and this is the DCM for input inductor design, and this is the capacitor for energy transfer values, like for both positive negative half cycle, both are identical, and this is the output capacitor for second harmonic ripple, how much you can permit. So, that is virtually the design equation, based on that you can design it, and this is the second version of this bridgeless power factor correction bridgeless SEPIC converter, for positive negative half cycle. This is the third, you can call it the topology corresponding to your bridgeless version, and this is the fourth topology of SEPIC, your bridgeless SEPIC converter with again power factor correction, and this is fifth topology. You can see fifth topology of your bridgeless SEPIC converter like, and these are the typically for the fifth topology. You can see the supply voltage, supply current, your DC link voltage, and the inductor current, input inductor current continuous, then the output inductor current discontinuous for positive negative half cycle, capacitor voltage, energy transfer capacitor voltage, positive half cycle continuous, and switch voltage, switch current, and this is the TAD of only 1.95% for 800 watt, and output voltage 300 watt and 220 volt supply like. So, coming to like a analysis, design and simulation performance of power factor correction bridgeless Zeta converter. Coming to Zeta converter, this is first topology for positive half cycle and negative half cycle, that is bridgeless version, no diode bridge is there. So, this is the output voltage, and this is the output inductor for continuous conduction, this is input inductor design for continuous conduction, and this is boundary condition for which you have to keep for DCM less than that for output inductor, and this is the output input inductor for DCM if you want to design, and this is the energy transfer capacitor for this Zeta converter, and this is the output capacitor calculation corresponding to second harmonics and ripple voltage, which you really have for capacitor design for output, and these are the typical for design for 800 watt with the output voltage of 300, and you are getting TAD 2.1% with the supply voltage, supply current almost in phase and almost sinusoidal current, and input current continuous for positive half cycle, negative half cycle, and the output inductor discontinuous for positive and negative half cycle, capacitor voltage continuous for positive and negative half cycle, and with the TAD quite low of 2.12% like and this is of course the second topology for Zeta converter, for bridgeless Zeta converter also. Coming to like a design simulation performance of PFC bridgeless canonical switching converter. So, these are topology, first topology of canonical switching converter for positive half cycle, negative half cycle, and this is the relation for output input voltage, the input inductor, typically inductor design, the transfer capacitor design, and the input inductor design, the inductor design for DCM, this was for CCM, and output capacitor design like for a given voltage ripple here like and these are the typical experimental result for 350 watt converter with the output voltage 200 volt and 220 volt supply. So, this is supply voltage, this is the, you can call it the inductor current for positive half cycle, negative half cycle, and the capacitor voltage for positive half cycle and negative half cycle, continuous voltage and inductor current discontinuous, and this is the performance with the TAD of 3.7% of supply current and power factor unity. You can see the supply voltage and supply current is quite good waveform like with the power factor correction unity like here, and thank you.